Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. My name is Wan Ismail bin Ibrahim from Faculty of Electrical and Electronics Engineering Technology, University Malaysia Pahang. So today I would like to present one part of our research. The title is Modeling of Power Curve Equation for Small Scale Vertical Axis Hydrokinetic Turbine. Energy demand is significantly expanding over the year due to the economic prosperity, enhance of the living life, and also increasing the number of population worldwide. Conversely, the high price of conventional fossil fuel, limited reserve capacity, and environmental issue due to the high CO2 emission are the primary concern nowadays. Therefore, clean, safe, and reliable energy resources are required for energy sustainability for the future development. Okay, the hydrokinetic technology is one of the best options to provide a clean, safe, and also sustainable energy for the future generation. Okay, what is hydrokinetic technology? The hydrokinetic technology is an electromechanical device that able to convert the kinetic energy of water flow into electrical energy through the energy conversion scheme and power electronic converter. Okay, as long as the water is flowing, so we can harness the electricity. Kinetic technology. First, the technology is only give minimal impact to the environment and ecosystem because the system can be operated without any reservoir. The system only require a minimum civil work and can be deployed along the riverside by a floating pontoon or by a fixed structure. The most important thing is the concept and operation are similar to the wind turbine system, okay, in terms of the hardware requirement, control, the turbine, okay. Then even the output is small, the capacity can be increased by using an array system. Okay, what is power curve model? Okay. Power curve model represent the characteristic of the turbine. Okay, each turbine has their own characteristic. For example, we have a different type of turbine classification. We have the vertical axis turbine, we have the horizontal axis, we have the cross flow turbine, which each turbine have their own characteristic with their different power coefficient and tip speed ratio. Other than that, the turbine characteristic is also depend on the turbine size, number of blade, and also type of airfoil used at the turbine blade. Okay. However, the most important thing is the power curve equation is applied to determine the turbine performance. Okay, the the capacity factor estimation, the turbine selection, as well as the energy generation forecasting, especially in wind energy conversion system. Okay, what is the motivation of this study? Okay, the development of the hardware or prototype for the hydrokinetic energy harnessing is time consuming, okay, and it's very complicated. Therefore, by modeling the turbine into an equivalent mathematical equation, we can provide a better analysis of the system requirement. For example, we can reduce all the time, cost, and also the error. As far as the author are concerned, an equivalent power curve model to represent the hydrokinetic turbine in the river is rarely presented in the literature. Therefore, in this study, we have simulated the characteristic of the vertical axis H Darius turbine, and we developed the power curve model based on the numerical approximation techniques. Okay, based on the literature review, there are a lot of study regarding the power curve equation, especially in wind energy conversion system. Okay, as can be seen here, there are a lot of power curve model equation because the turbine have their own characteristic. Okay, depending on the sizing, depending on the number of the blade, and also type of the airfoil. For example, the equation by the Miller here, okay, is only applicable for the large turbine system, and it's not suitable for the small scale turbine. Okay, for the methodology, first we begin with the assessment study at the potential resources. Okay, back in 2018, we were conducted a sampling measurement at Pasir Kubu River, Sungai Lembing, Kuantan, to study the river characteristics such as the river depth, water velocity, cross section, and so on. Okay, then next step, we determine the turbine sizing. Okay, so in this project, we have decided that we need the produce 200 watt output power because based on the literature, uh, 200 watt is sufficient for the standalone and also for remote community. Okay, next step is to simulate the turbine using the kubelet software to see the pressure distribution. Okay, pressure distribution around 300-degree angle of attack on the turbine blade. Okay, this analysis is required to generate the power coefficient or CP curve of the turbine. Okay, then next step is uh, we using the MATLAB MATLAB to generate a polynomial approximation equation through the curve fitting. And then lastly, to choose which equation or which one is better, then we using the root mean square error RMSE to find the most suitable polynomial equation to represent the power curve model for the H Darius turbine. Okay, for the result, so this is the CP power coefficient versus tip speed ratio TSR of the H Darius turbine. So by using the numerical approximation technique, we generate the polynomial equation which consists of the 4, 5, 6, and 7 degree of the polynomial approximation equation. Okay, as can be seen on the figure, the the equation for the 4 and also 7 swing to the positive region when it reach TSR equal to the 7. Okay, on the other hand, the equation for 5 and 6 oscillate or swing to the negative region when it reach to the TSR equal to 7. So from here, we cannot determine which equation is the best to represent the H Darius turbine. Therefore, to choose the best polynomial approximation equation, so we have applied root mean square error, which is we have calculate all the error for each curve, and based on the RMSC value, the sixth polynomial equation has been chosen due to the least value of RMSE, which is a 0.1165. Okay, as for the benchmarking, the proposed turbine power model based on the H Darius turbine, okay, 6 polynomial equation has been compared with the equation 6 by the N ordinary. Okay, as can be seen in this table, uh, we have compared in terms of the mechanical power and also the efficiency. It shows that the H-Darius turbine, based on the six polynomial equation, uh, has the highest efficiency compared to the equation number 6 by N ordinary. Okay, this is the model of the hydrokinetic turbine. So we can calculate the mechanical power using the equation half time rho times A strike area V cube times Cp power coefficient. So this is the V water velocity V cube, water density rho, strike area is A, and also the constant 0.5 here. So where is the Cp? Okay, this is the function of Cp. We can implement the power curve equation into the MATLAB function here. So this is the main contribution of this paper. We applied the six polynomial approximation equation. So this is the equation for the six polynomial equation to represent the characteristic of the H-Darius turbine. Okay, for conclusion, in this research, we have proposed the power curve equation model based on the polynomial approximation equation to represent the H-Darius turbine characteristic. Then we have choose the six polynomial approximation equation uh, has been chosen due to the minimum value of RMSE. Then the efficiency of the power curve equation model is achieved 86.92% compared to the benchmarking model. Then for the future work, this power curve equation model will be implemented in the turbine model to study the MPPT algorithm and also the control strategy for small scale hydrokinetic technology. Okay, that's all from me. Any question regarding to this research, kindly please email me at wismail@ump.edu.my. Thank you.